we can use Myhill Nerode theorem to prove that some language is not regular. So far we have used the pumping lemma, either the usual one or the generalized one, to prove some language L to be non-regular. But now that we know Myhill Nerode theorem, this gives us another method to prove a language not regular. For example, consider this language 0n, 1n. We know that this language is not regular. We proved its non-regularity by the pumping lemma. Now, the way we use Myhill Nerode theorem to prove non-regularity is this. Recall, we have one thing that Myhill Nerode theorem says, that L is regular if and only if RL is of finite index. In other words, the equivalence relation RL for language L, if you consider that, then if the number of equivalence classes is infinite, then the language is not regular, and if the number of equivalence classes is finite, then the language is regular. In this case, it is fairly easy to show that RL for this language will have infinitely many equivalence classes. Let's consider sets of strings like this. Ek is 0 n 1 n minus k. And of course, k is less than equal to n. Now, take two strings from two different EKs. So, let us say EK1 and EK2. I claim that a string, so let us write it here. Let us say x is in EK1 and y is in EK2 and K1 is different from K2. So, consider this string x1 K1. So, remember what is x? X will have some n number of zeros and some number of ones which is less than by K1 from the number of zeros. And if you add this K1 once after x, then clearly this will have equal number of zeros and ones. Therefore, x1 to the power K1, this string will be in the language. Whereas, if you take y from EK2, the deficiency number of ones it is less by is K2 and K2 is different from K1. So, this will not be in the language, right. So, therefore, from here we find that x and y, so as any string from EK1 and any string from EK2 must be in different equivalence classes of RL. Then it is not difficult to see now, since we can have infinitely many keys, this means that we will have infinitely many sets like this, such that if you take two different such sets and you take two strings, one from here, one from here, they cannot be in the same equivalence class, they must be in different equivalence classes, and therefore, number of equivalence classes of RL for this language must be infinite. Therefore, this proves that the language L is not regular. So, this is a direct application of Myhill Nerode theorem to show a language to be not regular. Let us now consider this topic of minimization of states of DFAs. So, what is the problem? We have a DFA M we would like to find out a DFA M dash such that both M and M dash they accept the same language, and of all DFAs accepting that language, M dash has the minimum number of states. Now, the first thing we need to appreciate that even for this problem, Myhill Nerode theorem tells us a way of going about. Let us see how. So, L is, let us say L is a language, and M is a DFA to accept it. Right. Now, you recall the definition of RM. What was RM? We said, starting from this machine definition M, we said that two strings X and Y are related by this if and only if both X and Y take M from its initial state to the same state. Okay. Now, we can write it in or the symbols that we are familiar with. Suppose M is Q sigma delta Q0 and F, then how many equivalence classes RM will have? RM will have exactly so many equivalence classes and one for each state. And we remember that corresponding to state Q, let us say small q, the equivalence class, maybe I can call it as AQ, is the set of all strings X in sigma star such that delta hat Q0 X is Q, right. So, what it means is sigma star is partitioned into equivalence classes, and each equivalence class corresponds to one of the states of the machine N. Now, what is the best machine for this language L? Now, it is not difficult to see if we go back to Myhill Nerode theorem. Any machine, so for the language L, a machine, a DFA, let us say M1, has minimum number of states a DFA M1 has minimum number of states. Of course, this DFA has to accept the language L. If and only if the equivalence relation corresponding to this machine RM1 is exactly equal to the equivalence relation RL. In other words, what we are trying to say is this, that X for all X, Y in sigma star, X RM1 Y, this holds if and only if X RL Y holds. Why is so? Because remember that any machine to accept L gives rise to, of course, an equivalence class Rm, and what we have proved in Myhill Nerode theorem, that Rm is what we call, that it is, so let me get a picture. So let us say this is sigma star, right, and let us say, for we are just taking an example, RL is partition sigma star, let us say in these many equivalence classes, and remember that the language L has to be one of these or a number of this union of some of these equivalence classes. So, for the purpose of illustration, let us write, let us say that this particular equivalence class, the strings in this, they constitute the language L, right. This is my L, and of course, the other strings are not in the language L. Now, if we provide any machine, any DFA to accept L, Myhill Nerode theorem says that the corresponding Rm for, so let us say M to accept L has to be a refinement of RL. That means what? If you go back to the definition of the refinement of two equivalence relations, see, Rm is an equivalence relation, RL is another equivalence relation, and we said that Rm is a refinement of RL if the equivalence classes of RL are such that they are basically obtained by breaking one or more equivalence classes of RL. Actually, I should have said 0 or more, because if M is your best machine, then RM equivalence classes will be same as RL equivalence classes. So, in other words, if the machine M does not have the minimum number of states to accept the language, then it means that RM will essentially partition some of the equivalence classes, will break up some of the equivalence classes. So, let me show that situation in this manner. Let us say by this colored thing, what we mean is, now previously RL had 1, 2, 3, 4, no 1, 2, 3, 4 equivalence classes. Now, this particular equivalence class of RL is partitioned into 2, and this is one equivalence class of RM, this is another equivalence class of RM, and similarly here. Maybe more things are broken up, but this picture will suffice to make our point. And this is the general understanding of refinement. RM is a proper refinement of RL. That means that it breaks up some of the old equivalence classes of RL for its equivalence classes. So, what would minimization mean? Minimization would mean that right now I have two states. Recall that for every state of the machine M, we had an equivalence class in RM. If it is a proper refinement, RM is a proper refinement of RL, that would mean what? Two or more equivalence classes corresponding to therefore two or more different states of the machine M. All of these actually fall in the same equivalence class of RL, right. So, for example, here that maybe this particular equivalence class corresponded to state Q1, and this particular equivalence class corresponded to the state Q2. And what is their relation? Their relation is that the equivalence class in RM corresponding to the state Q1 and the state Q2, both these classes are subsets of the same equivalence class of RL. So, if there is a way of combining these two states, then of course it would mean that this line would go, this pink line would go, and we will have improved in terms of the number of states in the DFA accepting the same language. So, this is why we are saying that for the language L, a DFA M1 to accept L has minimum number of states if and only if the equivalence classes corresponding to that machine RM1, they are exactly the same equivalence classes of RL. If not, it would mean the RM1 is a proper refinement of RL, and therefore, this kind of possibility of combining two equivalence classes, two of its equivalence classes into one is there, and thereby the possibility of reducing the number of states is there, right. So, now we can see what is our problem for minimization. We have been given a particular machine M. We have been given a DFA M. can I find two states repeatedly in this machine M such that the equivalence classes corresponding to these two states, equivalence classes for Rm corresponding to these two states, both of these equivalence classes, they are parts of the same equivalence class of RL. How do I identify such pairs of states? The question we are asking is, for this machine M, let us say M is again as before Q sigma delta Q0 F. The question we are asking is, can we identify Q1, Q2 in Q such that the equivalence classes corresponding to Q1, Q2 are both subsets of the same equivalence class of R. Now, it might appear a little confusing because we are simultaneously talking about two different equivalence relation. When I say can we identify Q1, Q2 in Q such that the equivalence classes corresponding to Q1, Q2. Now, here we are talking of the equivalence relation Rm. So, let me write it clearly such that in Rm the equivalence classes corresponding to Q1 and Q2 are both subsets of the same equivalence class of RL. Now, so then you can see then you can see the picture. So, this is Q1, this is Q2, something like this, and therefore, at least intuitively we see that we can do something to merge these two states and thereby will improve in number of states. Now, what is easy, in fact, what is more direct and equivalent of course, to identify pairs of states which are not so. In other words, let us look at this. What we are saying is that Q1, Q2, another way of saying this, that we are trying to identify this pair Q1, Q2 is distinguishable. This is the term used to mean that the equivalence class in Rm corresponding to Q1 and the equivalence class corresponding to Q2 in Rm, these two equivalence classes are not subsets of the same equivalence class of RL. So, if the equivalence classes in Rm of Q1 and Q2 fall in different equivalence class of RL. So, this is the definition of this term distinguishable. I say a pair of states is distinguishable if this holds. Now, this holds when? That we know. See, what do we know? When will two, So, let us say now that AQ1 is the equivalence class corresponding to Q1 in Rm, of course, and AQ2 is the equivalence class corresponding to Q2 in Rm. So, when are they not in the same equivalence class of RL? So, the situation is this is Q1 and maybe not Q2 here, but if you take something like this, this was your Q2, then this equivalence class and this is your AQ1 and this is your AQ2, and they are of course in two different equivalence classes of RL. And such pairs of states are easy to see or easy to figure out, at least we have a definition, because they are in two different equivalence classes of RL. So, a string from here, let us say, what can I say about, suppose that x is in AQ1 and y is in AQ2. Now, suppose that x is not not in the same, not related to y by the equivalence relation RL. That means, the equivalence class in which x is there and in which y is there, these two classes fall in different equivalence classes of RL, and that is what was this question. So, that is how to answer, right. And what do I know about AQ1 and AQ2? AQ1 are all those strings which take m from Q0 to the state Q1, and AQ2 are all the strings which take the machine m from Q0, the initial state, to the state Q2, right. Now, let us write this in terms of the machine behavior. So, let us summarize what we are saying. This is a machine m, Q1, Q2 are two states in the machine, and equivalence class AQ1 is an equivalence class corresponding to the state Q1 for the equivalence relation Rm, and that by definition is this. We had seen the definition of Rm. It is the set of all strings which take the machine from its initial state to Q1, and similarly for Q2. Now, what we are saying that these two states are distinguishable if and only if these two equivalence classes are in two different equivalence classes of RL. And how can I figure that out? Now, look at it this way, that suppose there is a z, some string z, such that delta hat let us say exactly one of delta hat Q1 z and delta hat of Q2 z. Remember, these two will be two states. What we are saying, that suppose there is some string z such that exactly one of these two states is in F, and basically that means the other is not in F. consider this situation. So, there is some string z such that delta hat of q1 z, let us say it is one of the final states, and delta hat of q2 z is not a final state. But what does it mean? Let us say string x took the machine, as we said, suppose from q0 to q1, and now consider this z. So, now let us say, so suppose x, this string x is in aq1 and y is in aq2, right. Suppose this is the situation. Then now look at these two strings xz and yz. So, of course, x is in the equivalence class aq1, and now you applied this string z as a concatenated string to x on its right, and similarly you did for yz. And now what do you find? That totally, if you take this string x z, x took the machine m from q0 to q1, and then from q1 z took it to, let us say, final state, and whereas y took the machine from its initial state to q2, and then the same z took the machine to a non-final state. That means what? That means this string will be in the language and this string will not be in the language. That means what? That the two strings x and y is not related by the relation, equivalence relation RL, and therefore, of course, it means that AQ1 and AQ2 are in two different equivalence classes of RL, and that is why this is the situation in which we can say Q1 and Q2, this pair of states is distinguishable. And coming back to what we were saying earlier, it means that there is no way we can merge these two states and hope to get a DFA which will be accepting the same language, right. However, you see that this is now, at least it seems that given a pair of states, look at this situation, what we are saying, that suppose there is a string z in sigma star, that exactly one of these two states is a final state. This is something we can test, as we shall see, by means of an algorithm, and thereby we will be able to figure out all pairs of distinguishable states. And from what I know from Myhill Nerode theorem, that such pairs of distinguishable states, if Q1 and Q2 are distinguishable, that they cannot go into the same equivalence class of RL, and the best DFA, or the DFA that will correspond to, whose RM will correspond to RL, that will be by somehow combining those states which are not distinguishable. So, let us now spend time to find out how we can test this condition. So, we have motivated ourselves towards this definition of distinguishability for a pair of states. What we are saying is that a pair of states is distinguishable if you can find a string z such that exactly one of delta hat q1 z, this is one state and this is the other state going from q2 to z using z, exactly one of these states is in F. In such a case, if we can find this condition to be true for a pair of states, we will say that pair of states is distinguishable. And there is a systematic way of finding all pairs of distinguishable states. First of all, one thing is very clear, that if one of Q1, Q2 is in F and the other is not, then Q1, Q2 is distinguishable. Why so? Because in that case, in this situation, so what is the situation? Let us say Q1 is in F, one of the final states, and Q2 is not F. Then this pair is distinguishable. That is because, consider Z to be epsilon, the empty string. Delta hat Q1 Z, Q1 epsilon is Q1, which is a final state, whereas delta hat of Q2 Z, Z is epsilon, this will then be, when Z is epsilon, it will be Q2, and Q2 is not final state. In that case, of course, this pair is distinguishable. So that's how our algorithm would start to find out the set of all possible pairs of distinguishable, all possible distinguishable pairs of states. Outline of algorithm to find all pairs of distinguishable states So the initialization will start from this observation. So let us see what is the desired output. Output should be the set of all, the set S, let us say, of all pairs of distinguishable states. So this is the set that I would like to construct given a machine M. So initialization for S, will build S iteratively. So initialization is from this observation that S is all PQ such that on one of P or Q in F, the other not. So I have a first approximation to my set of all distinguishable states. Now let us see how we can, starting from this initialization, how we can augment this set iteratively. So this is the iteration part. Consider R1, R2, which a pair of states which is not already in S, and we will add R1, R2 in S. So we'll augment our set S by this new pair if for some A in sigma, delta R1A and delta R2A, this was in S. In other words, what our iteration is, consider all pairs R1, R2 which are not already there in S. This pair R1, R2 will be in, will put this pair also in S, provided I find some symbol A such that this pair was already there in S. What is the justification? Suppose delta R1A is P and delta R2A is Q, which means that PQ was already in S and therefore they are distinguishable. So, there is a string Z such that delta hat of PZ, let us say, is in one of the final states, is one of the final states, and delta hat of QZ is not. And now consider the string AZ. A takes R1 to P and rest of the string Z takes P to a final state. Whereas this same string AZ, what its behavior with respect to R2? R2 goes to Q on this symbol A, and from Q this string Z takes the machine to a state which is not final states. So, here is this string AZ which is such that exactly one of this will take R1 of the two states R1 and R2. AZ is a string such that it will take the machine to a final state from exactly one of these states R1 and R2, and therefore R1 R2 is distinguishable. So, this is the justification. Let me rub this out. This is the justification part, and our algorithm therefore will mean that in the iteration part you are considering all pairs of states which are not already in S, and such a pair you will add to S. If you find some symbol A, remember that number of symbols in sigma is finite. So, one after another you test this condition. You have chosen a pair R1, R2 which is not in S, consider delta R1A and delta R2A. This pair, ask, is it already in S? If it is in S, then put this pair also in S, and so on. And finally, we must say when to stop. So, we say that stop the process if in an iteration no new pair is added to S. Okay. So, remember the iteration is this entire thing. So, maybe just to emphasize this, I should write, consider each R1 R2 not in S. So, in one iteration, remember in an iteration you already have a set of pairs which is in S and some of the pairs which are not in S. These are the set of all pairs of states. So, in one iteration you will consider all the elements which are not in S, and as you consider one pair you may find this condition to be true. So, in that case that pair will be added and so on. Now, imagine an iteration where all the pairs which are not in S, you tested this condition and you couldn't put this any new pair, that pair to S. That was true for all the pairs not in S. In that case, we say that iteration did not add any new pair to S, and in such a case will stop the algorithm. What is the time complexity of this algorithm? It is fairly easy to see that this is a polynomial time algorithm, because in each iteration, how many total number of pairs of states are there? If there are n states, there are n square pairs of the order n square pair. Actually, n choose 2 pairs, and actually we should talk of unordered pairs, right? Because these are, if PQ is distinguishable, then QP is also distinguishable, but that is a detail. The main thing is, in each iteration we add at least one new pair. So, how many total number of iterations? So, let me write here the time complexity of the algorithm, and then we will bother about the correctness. Time complexity there are at most order n square iterations. And what do you do in each iteration? In each iteration you consider all the pairs which are not in S, and there can be order n such pairs which are not in S, order n square such pairs not in S, right? And you do something, you do this test for each such pair. So, you can see that in each iteration we do at most order n square operations. So, therefore, the algorithm is polynomial time. But this, what I said, is kind of pessimistic, right? You should be able to see that the algorithm really, the way I have said, as if it is order n4, but actually it is order n cube. Just to make this point that it is polynomial time, I made this rather loose argument, but you should be able to see this, that this is actually order n cube, though from what I have said it does not immediately follow. You should be able to do this, check, right? Check that this is indeed order n cube. And now let us talk about the correctness of the algorithm. So, let us see why the algorithm that we have outlined is indeed correct. When is it correct? If when we stop, by then we would have discovered all pairs of states which are distinguishable, right? We end with a certain set S, and if that S contains every pair of distinguishable states, then of course the algorithm is correct. So, I would like to show that is indeed true, and let us prove this by contradiction. Suppose our algorithm is not correct, then then they must exist, then for some instance, and here the instance is of course you are given a DFA, then for some instance when the algorithm ends, there are pairs of states, pairs of distinguishable states which are not in S. Right? That is why the algorithm is incorrect. So, incorrect means this condition must be true. There must be some instance where it is working incorrectly. That means it has not been able to complete the entire set of, it has not been able to put all the set of distinguishable states into distinguishable pairs of states in S. Right? Now, let S prime be the set of distinguishable states pairs of states not in S. So, these are S prime are all those pairs which ought to have been in S, but they are not in S. Right. So, supposing these are these pairs P1, P2, or let us say P1, Q1, P2, Q2, and so on. And now, suppose for each one, let us say we say for each Pi, Qi, each such distinguishable pair which is not in S, let Zi, let Z1, so in this case Zi. So, these are strings, and what are these strings? They distinguish these pairs. These are the shortest. So, let Zi be the shortest length string such that exactly one of Pi Zi and Qi Zi is in F, right. So, that means these string Zi witnesses the fact that the pair Pi Qi is distinguishable, and we are saying that Zi be the shortest length string of all such pairs. Of all such strings, there will be infinitely many strings. Let Zi be the shortest. Now, let Z be the shortest of all these strings. So, in each Zi is shortest witness for that corresponding pair, and of all these, let particular Z be the shortest of all Zi's, and let Z correspond to the pair PQ. Right. So, now let the string Z be some A followed by some, let us say, Z dash. That is the string Z begins with the symbol A, right. Now, consider this pair of states delta P A and delta Q A. Now, let this be the state R1 and let this be state R2. Now, I claim that R1, R2 is, of course, is firstly two things I claim is distinguishable and R1, R2 is in S. That means R1, R2, this pair, this distinguishable pair would have been discovered by our algorithm. Why? The answer is, the reason for that is very simple, because the fact that R1, R2 they are distinguishable, that is witnessed by Z prime, because if you go from R1 on Z prime, say let us say this from P on A goes to R1 and R1 on Z prime goes to, let us say, final state, and this does not. So, R1 and R2 will be distinguishable, and a shorter string, shorter than Z exists. So, in that case, that would have been the pair R1, R2 I would have picked up, and Z prime would have been the Z and not this Z. So, this is true, R1, R2, this pair is distinguishable, of course, that is easy to see, and what more, this pair is already in S. And now comes the contradiction, that consider, so since R1, R2 is in S, it means this pair R1, R2, this pair R1, R2 was included, came in S sometime in the algorithm, maybe in the initial phase or maybe in one of the iterations. So, now consider the iteration immediately following that, when R1, R2 came into S. By then, the pair PQ would not have been in S. In any case, PQ is never in S, right? PQ was missed by our algorithm. But when you take the pair PQ and consider the symbol A, then you would have got the pair R1, R2, which was already there in the set S, and then PQ would have been declared as distinguishable. So, therefore, we have a contradiction, and therefore, this is not true, that there is some pair of distinguishable states which our algorithm had failed to discover.